All right, so we're going to relate today Gibbs free energy and equilibrium, and this is the last equation in your thermodynamics section.
Let's go.
And it will put together delta G with K now. So it's one equation that you're going to learn for this entire lecture, and then we're going to practice a bunch of problems, and then tomorrow we'll just continue to practice. It is not hard, but there's ways that you'll make a mistake. It's just a calculation. You get one equation, and you just learn how to use it. But there's things like being a joule fool you have to be aware of, and you have to also evaluate the number without a calculator. So we're going to practice those things just this lecture. We're going to practice that. So first thing is, what do we know about delta G so far? And we know that it has to be less than 0 for a reaction to proceed in a given direction. Now so far, all I've been saying to you is that delta G has to be negative, right? And then the reaction is spontaneous. And you think if the delta G is positive, then nothing happens at all, right? It just sits and does nothing, like it's just not going to occur. That's not entirely true. Equilibrium exists on everything, right? That's why we write a double way arrow. It's just that some things will go predominantly to products, and then some things will stay predominantly as reactants. So we're going to evaluate how delta G relates to equilibrium in that sense. And then finally, delta G is the maximum amount of work that is available, or energy available to do work. And then if there's no energy left, if there's no work left, you can't do anything. So when the system is at equilibrium, the system cannot do any more work, so delta G equals 0. So say you have a system that is proceeding, delta G is negative, 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 and then all of a sudden you use up all of your energy and there's no more left, so you can't do any more work. Get it? So it's negative up until a point, and then it turns to 0. Once you reach 0, to do any more work would be positive. And that's why it doesn't continue to happen, because the universe won't allow positive delta G. Although forward and reverse reactions continue to take place, changes in concentration aren't possible, so you can't go and continue to make products because there's no energy available to do work. So KEQ is directly related to delta G. So this graph is just showing you visually what happens in a reaction. So you have A going to B, and we say that if delta G is negative for this process, we make B. But now we know that we don't make predominantly B, we make some amount of B, right? But we could also end up with making some A and not that much B, like more A than we make of B. So this is what this is showing you. This is your delta G value here. So 0 up to some number. It's not labeled for you. And then this is the amount of A and B. So you start off with only A in your vessel, and then you're hoping to get to all B at the end of it. So as the reaction progresses, delta G, there's energy available to do work, right? But that energy starts to go down because it's being used to make B. And then it's continuing to be used, and then all of a sudden I run out of energy to do work, and it stops, and delta G is equal to 0. And this is my equilibrium position. Because you cannot make any more B, because now to make B would require an upslope to get to delta G, right? So if you consider this as your delta G final, my final spot here is delta G equilibrium, minus my delta G initial, take this value, pretend that this is, I don't know, a 3, and this is a 10. So 3 minus 10 would give me a negative number, right? Negative 7. But if I wanted to go from this final position, G final minus, G equilibrium, say that's like 5, and this is my 3. Now that's a positive value, a positive 2. I'm just making up numbers to help you see it. So that value would be delta G here would be positive, delta G coming down is negative, which means that your reaction will proceed until you reach equilibrium and then it stops. And that's why you don't make any more products, because you have no more energy available to do work. If I try to go in the reverse direction of this reaction, is that possible? No, because to go backwards now would require a lot more energy, and you don't have it because that's an upward slope, because your final would be here and your initial would be here. So delta G is negative up until you reach equilibrium. Once you reach equilibrium, delta G is 0. So on this next little piece, it just shows you that that upslope here is positive delta G, and this downslope is negative. So I could start my reaction with B. As a chemist, I could take a reaction vessel and just put in my B, but that will only make that much A. right? Because that delta G value is only negative up until this point, and then it stops. There's not as much energy. So the overall delta G for this process is negative. Because if you take your G final minus your G initial, this is somewhere around 5, that was somewhere around 10, so 5 minus 10, I still get a negative value, right? So we say that a reaction is spontaneous if delta G is negative and it proceeds to the right meaning products. But now that you understand equilibrium, you don't make 100% products, you end up somewhere on the product side. So we call this product favored, right? Just like we use that word with equilibrium. Now if we switch this reaction, let me just go over this first. So if the process favors products at equilibrium, then delta G is 0. So just right here, delta G is equal to negative. So if delta G is negative, then that means that the reaction is going to proceed to more products. If you proceed to more products, then your K value means that this will be greater than 1. See how I came up with K greater than 1? Because I know that delta G negative means that I make products, right? This means products are favored. So if I know that means products are favored and I write my K expression to always be equal to products over reactants, then I know that that means that my numerator is going to be larger, which means that K will be greater than 1. And you already know that if K is greater than 1, then that means that it's products favored, right? So see how I related the two? And then it says the reaction will proceed to equilibrium in either direction. The reaction is considered exergonic, which means that there's free energy available to do work. Exothermic means energy is released in the form of heat. This is exergonic, energy is released in the form of work. So on this part, this is just the opposite. So I've sort of been telling you all along that if delta G is positive, that means that the reaction doesn't happen, right? It's not spontaneous. That's true up until the equilibrium point, right? And when we say a reaction is not spontaneous, it's because it ends up producing so few products that it's not considered really going to a reaction. So when you look at this slope, and you look at the final G and the initial G, your G final minus your initial, here is G final, minus here your G initial, this will give you a delta G that's positive. Do you agree? Yeah. So then this overall reaction is not going to be spontaneous, which means it's not going to be product favored. So when you get a positive delta G, that means that it's reactant favored, and that equilibrium lies far to the left. So that's kind of the phrase that we would use. Equilibrium lies far to the left. The left meaning the reactant side. So heading down the slope is negative. Heading back up that slope would be positive. And once I reach equilibrium, delta G is equal to 0. So at some point I have a little bit of my products being produced because I'm going from pure C to pure D. I have a little bit of product being produced, but to make the rest of the way to go to products is so non-thermodynamically favored that it's not going to happen. So the overall process is not thermodynamically favored, but you still have a little bit of the reaction progressing. Does that make sense? So for a process that is positive, if delta G is positive, what does that mean to us? That it's not spontaneous and that it's reactant favored. If it's reactant favored, then our K value here, we always write products over reactants so that we can see that. That means that it's reactant favored, this is big, and then K will be a small number because your denominator is large. So K is less than 1. Do you see how you relate them? Yep.
Can you restate the definition of exergon?
It's free energy. Like free heat is exothermic because therm means heat. Exergonic is free energy.
Energy available to do
To work. Yeah.
That's it.
Mm-hmm. In other words, endogonic, I guess is how you would say it, is it's going to use energy up, And you wouldn't have energy, really, if delta G is positive. There's no energy available to do work. All right, so if K is less than 1, the reaction will proceed until it reaches equilibrium. Once it reaches equilibrium, delta G is 0. A process that is not thermodynamically favored, delta G is positive, will produce products if the system initially contains only reactants. If the products are removed, the equilibrium will shift in order to produce more products like Chatier. So here's, like, again, engineering 101. You could have a really non-thermodynamically favored process, and you want to make a certain product, but it's not favorable. It'll make a little bit of that product, but you can make it make a whole lot of product because you could keep removing the product. You either could precipitate it out so that the concentration is not visible to the K expression, or you could remove it by decanting it or using some other process to get it off. And then your system would continue to make more and more products, even though the equilibrium lies far to the left. Does that make sense? So what I'm showing you here is that at equilibrium, delta G is always going to be equal to 0. Because you just used it all up. You used all of your available energy to do work, and then there's no more energy available to do work, so the reaction stops at equilibrium. All right, what is delta G naught again? What does the naught symbol mean?
25 degrees.
It means 25 degrees Celsius, 1 atmosphere, and 1 molar concentrations, which we haven't really used yet. Except that the AP exam and scientists do this, where they write delta G naught, and then they're like 350, or they'll write delta G naught, and then they'll put like 750. In other words, this is the temperature in Kelvin of the experiment. So we know that the K value changes, don't we, at temperature. So the delta G values would be different at different temperatures. So they're saying to you, this naught symbol really just means 1 atmosphere and 1 molar concentrations, because if I put the temperature down here, then it's not at standard temperature. So this naught symbol just really means 1 atmosphere and 1 molar concentrations. And so they can tell you the temp here. Temp given. So that's all this slide really says. Like, you can read it extensively. It just means that delta G naught can be given at different temperatures. Yes?
What is 1 M again?
Molar. In other words, molarity, so for concentration. Okay. This is the equation that we need to focus on for the rest of the lecture. This is given to you. This is not given. So if you look at your equation sheet, you're only going to see this equation and not this equation. So let's go over some basic concepts that you know already from math class, but I have to remind you. So if I have, let's say, x to the negative 1, what does that actually mean?
1 over x.
Okay, 1 over x. What if I have x to a negative number? So this means what?
X
To the number.
X to the number. Okay? What if I have x to a negative decimal?
It'd be a square root, or like a root of the.
Okay, so sort of like a root, but what do I do with it?
Isn't it like 1 over?
It's still 1 over x to the decimal. Right? And then if I have like a number meaning a whole number, x to a whole number, it's still 1 over that number. Okay, what does E equal? Does anybody know?
2.7.
Hey, good job. 2.7. We're going to stick with 2.7. Do you know when you use E? It's to get rid of a natural log.
I was just about to.
So you have ln. I have no idea how to write this for math class because I don't teach calc or any of those special things. So ln is to E. I don't know. You E it.
You eat.
You E it. You want to get rid of ln, you E it. It's not like you have x, so you divide by x to get rid of it. You ln it, so you E it. What is this swirl thing?
And then you have a
Like
log.
ln 4
4 equals x is really like ln to the whatever e to the x equals 4.
So then you start at ln to the x. Yeah.
Yeah, that's the arrow.
That's your swirl.
Because
So where do I swirl?
From ln to the x, no, ln. Start at the bottom of ln.
And then
go
swirl
around to the x.
To the x. No,
Oh, wait,
not
either
that.
way. You hit
To
the
the
x,
right, hit the x,
and then you hit the 4.
And the base of ln is always e. That's like the natural.
So e of x is 4.
And
And
called like the natural log e is ln, and then base e.
base e. That's the part, the base e. Because natural log is base 10.
And then, yeah, natural
Right,
log is
so, or log is base 10. Okay, anyway, you e it, people. So watch. Just algebra is all I'm asking you to look at. And the piece that you may not know is the e part, which we just kind of discussed. So here's what you have. This is your equation. If you want to get rid of it, we're looking to solve for KQ. So this is what's going to happen. You're going to get your thermodynamics lecture that I gave you your test on. And what you're going to do is you're going to solve for delta G using one of the processes that I taught you. So either you're going to use like your delta G equals delta H minus T delta S equation, or you're going to use delta G equals delta G products minus reactants. Then you're going to solve that in like a part A. So you're not getting rid of thermodynamics. You're going to use that for this exam. So you still have to remember all those equations, which is why it's important to get your test corrections done and ask for help on thermodynamics if you don't know how to do it. So you're going to use your thermo stuff for delta G, and then I'm going to say, what's the KEQ value? So now you're going to solve for KEQ. So you first divide by negative RT, right? You get that out. You divide this by negative RT. So right now I have delta G over RT negative is equal to ln KEQ. So what we just said is, how do you get rid of an ln? You e it. That's my own phrase. You e it. So I e it. I don't even know what to write there, except that you put e to that power. That's it. Just do it.
What?
What?
So you don't swirl. See, like if you swirl, it'll just
You
be
do
like
swirl.
E to that, yeah.
It's the same thing.
It's the same. I did too.
You unswirled.
Wait, so what do you?
You have to take your expression and you raise e raised to the negative G RT. But you cannot forget the negative sign. So I'm going to tell you what my students do. If you mess this up, you forget your negative sign. You forget to carry your G sign. So say delta G turns out to be negative, you forget to carry your negative. Or you forget to write the negative sign here. It's always the negative. The other reason why you mess up is because R is in joules, so delta G must be in joules. So you cannot be a joule fool. Those are the only two reasons why people make a mistake. On the last exam, nobody was a joule fool.
Yay.
Don't be a joule fool here. So you're going to have to make sure that your joules match, that the temperature is in Kelvin because you have Kelvin in your R value. Make sure you use the R 8.314 because that's the R value. So what you're going to examine now is how to solve this without a calculator. They do say that you're going to have to be able to estimate what your K values will be based on your delta G's, and it's not hard to do. So you're going to really pay attention to what I'm going to explain to you now. Got it?
So, our final answer is in joules or no?
No, KEQ doesn't have units. Your joules will cancel.
Does anything with a K have a
You could definitely work units out, but K expressions, the K constant, is just unitless.
So we're gonna find G in kilojoules, and then we just have to convert
Yes.
it to joules. Okay.
Yep. Delta G, remember, is always reported in kilojoules. So you're going to first have to convert your delta G to joules, and then you're going to have to solve for KEQ. All right, so now we're going to have to estimate what the value is of KEQ given some delta G values. So I don't know that I actually have seen this on a multiple choice exam because they don't release exams every year, the multiple choice. They only release the free response. They definitely put this on free response, but there's so many questions and I don't know what they all could be for you. So it's possible that you might have to do this just on a multiple choice exam. On my exam, you will. Got it? So here's how you evaluate this. If you have, well, first of all, you always have this expression. Your RT can always be estimated to be 2400 because the R value is 8.314, right? So I'm going to round that to 8. And my temperature is always 298, so I'm going to round that to 300. So 8 times 300 is 2,400. Do you all agree? So you're always just estimating your denominator to be 2,400. So then all you're really doing is evaluating E. So if E is raised to, now it's negative delta G over 2,400. That's what you're evaluating every time, which is why I did this whole thing with your X's for you, so that you could evaluate what happens. So let's take a look. If G is much, much greater than 2,400, that means it's a positive number, a big positive number. So I'm going to make a number up. I get 20 kilojoules, okay, 34 kilojoules. 34 kilojoules, I take that number, and I'm going to plug that in. So I have E raised to the negative, and now I'm going to plug in 34,000 joules. You said 34 kilojoules? So 34,000 joules over 2,400 joules per mole. Right? So just look at what your answer is going to be. 24 into roughly 340. So let's say 25 into 350. What's that? 4,
Like
8,
about
10.
40,
So
40, 10.
About
10, right?
Yeah.
That's what I thought. All right, so let's say that's roughly 10. Even if you don't know the number, you don't have to solve. It's not 10 because 24 times 10 would be 250.
Oh, yeah.
14. I missed a 4. Thank you.
40, 12.
I was counting probably like you. Like,
I'm good at
so 4, 8 gets me to 20. I missed the 300.
4, 8,
You like just do 350.
It doesn't matter. You really don't have to solve at all. My point to this, look, is that you know that this number is what? Greater than 1, right? So if I have a negative here, I'm saying this is 2.7 raised to the negative number. I have a whole number, right? So that's really just like 1 over 2.7 to some number. If you take 2.7 in your calculator and you even just get to 10, like 2.7 times 2.7 times 2.7 times, it gets really big really fast. Which means that this is what? Going to be a decimal or a whole number?
No.
Big decimal.
A big decimal, right? So if you get a big decimal,
No, you're right.
then your K value is much, much less than 1. What does much, much less than 1 mean?
You're negative. No. We'll be quiet now.
Your reaction is bigger than your
Yes. Do you get this?
Yeah, but wait, we don't have an answer.
We don't need an answer.
Oh, you
We
do.
will calculate it with a calculator at some point. But what the question's going to ask you is if you're product favored or reactant favored. That's what the question will say. So is this product favored or reactant favored? All right, listen to me. You are smarter than this equation because you know the answer before you start. If this is a positive delta G, is that product favored or reactant favored?
Reactant.
Which means that you should get a K value that's a decimal. So if you even throw this into your calculator and you don't get a decimal number, then you've messed up. Don't you agree? Like, I will often grade these and you guys will have the correct answer for delta G. You'll say delta G is positive. But then you get down to KEQ and you give me this massive number for KEQ, a positive KEQ, like a whole number. That doesn't make sense. Because a K that's much, much greater than 1 means product favored. But a G that's positive means reactant favored. They have to match. Follow that? Yes?
So I don't want to mess anyone up, but like you could look at the rough estimate and look at how big that denominator is, and from there tell how big your reactance is, right?
Yeah, that's what you're supposed to do. You have to evaluate this number. So if you're in between 2,400 and negative 2,400, which is sort of what you're saying, realize that this number here is going to be almost the same. So either it's positive 2,400 or negative 2,400, which just means that you're either going to get E raised to the negative 1 or you're going to get E raised to the 1. So you're either going to have 2.7 or 1 over 2.7, which is roughly going to give you your KEQ value of 1.
How much is roughly 1? Like how far does roughly 1 go out to?
These numbers, 2400 and negative 2400. That's what you're looking at. And that's easy to recognize because your RT value is 2400. So you're somewhere in the 2400 range. All right, the next part is if delta G is much, much less than negative 2400. So you have a big negative number here. What does that mean? Product favored or reactant favored? Product. So what should my K value be? Much greater than 1, right? But let's evaluate that with this expression. So if I have E raised to the negative, and now I have a negative delta G. So let's say delta G, sorry guys, I'm just going to go, is this over 2400. Recognize that you're now going to have a positive number, and it's E raised to a big number. So 2.7, say, times 10 to the 15th. So your K value will be much greater than 1, okay? No homework. All right. If you have delta G less than 0, so again, I would write the word or the symbol negative there, then you have mostly products. So evaluate that. If delta G is negative, that means that your reaction is going to proceed to products, right? It's spontaneous. It's thermodynamically favored, so it goes to product side. So if it's going to the product side, then products over reactants, products would be bigger, and then your K is greater than 1, right? But if it's much greater, in other words, it's below negative 20 kilojoules, which is negative 20,000 kilojoules, then you have much, much greater than 1, and therefore you're going to have virtually all products. So let's look at this as a multiple choice question. Don't call out the answer. So you have, you're choosing, is this somewhat reactant favored? Is it virtually all? Or does it lie somewhere in the middle? So you're given your delta H value, you're given your delta S value, and it says which of the following provides the best description of the system at equilibrium. So what should you be evaluating for this question? Delta G. So what equation do you have to use? Delta G equals delta H minus T delta S. And what should you tell yourself? Remind yourself, don't be a joule fool. Because S is in joules and H is in kilojoules. So evaluate this without a calculator. No calculators because this is multiple choice. All right, so I'm going to plug in. You can either go to kilojoules or joules for either of these. It's sort of up to you. But you have negative 20 kilojoules minus, and the T here is in that naught symbol. So that's 25,298. So I'm just going to plug in 300 times my delta S, which is negative 100 joules. Kilojoules, you move your decimal 3 to the left. So that's 0.100 kilojoules for delta S. So when I go to do this expression, if you're just really bad at math, you just put everything in scientific notation. 300 times 1 times 10 to the, and that's a negative first now, right? So 300 times 1 times 10 to the negative first is 30, right? So I'm going to put in 30, negative, and then this is negative. I forgot that. I did that before, too. This is a negative 0.1. So negative times a negative is going to give me a positive 30. So this is 20 kilojoules plus 30 kilojoules. This gives me 10 kilojoules. So either you've memorized the slide from the last slide that was up here, and you evaluate this, but I know that when May comes, I'm not going to be able to remember that slide. I probably will remember the 10 to the 4th slide. That one is always going to sort of stick. It's greater than 10 to the 4th, less than 10 to the negative 4th. But to remember that the 10 kilojoules is within that 20 kilojoule range, I'm not sure I would. So you could take this and further evaluate your K expression to determine where it mostly lies and relate that to your 10 to the 4th, 10 to the negative 4th. So if I did that and I related this, I would say E is raised to the negative 10,000 joules, right? Why did I convert to joules now? Because the equation is delta G over RT, and R is in joules. I could have. I just said that earlier. It's up to you. So if I put 10,000 joules over here, over, and this was my 2400. Now I can sort of evaluate that's about 4. So e to the negative 4 is what I'm looking at. Well, e is 2.17 to the negative 4th, so that's like 1 over 2.17 to the 4th. So I can sort of do that math in my head, can't I? And evaluate that this would be less than 1, but not virtually all. It's not going to be greater than 10 to the 4th. I put that in right. Right. So like 2 times 2 is 4, times 2 is 8, times 2 is 16, 1 over 16. That's not greater than 10 to the 4th, or 10 to the negative 4th. So what's your answer? Right, so if this is my delta G, negative 142,000 joules, it makes sense to keep it in joules because you know in the next part your R value is going to require you to use it in joules. So go ahead and throw that into that expression. And so I would say make sure that you get this answer right. Probably the biggest mistake on the exam, can you all just listen for a second, is that you calculate this number wrong, but you always get 1 point for the correct setup. This is what you don't get a point for. Even if you set this up correctly and you wrote, say, negative 142 kilojoules here, but you like intended on putting it in joules in your calculator, well, we don't know that when we're grading these exams, right? I just think that you're a joule fool, so you get no point for the correct setup. But you would get a correct point if you at least just wrote this out correctly. That was weird. If you just wrote this out correctly, I would give you a point here, and then maybe you lose the point for the answer. So make sure you write your expression out correctly. Yep.
Do you have to like do 8.1 smaller or 200?
What?
Like on the
You have to use all your numbers because this is short answer. You can't round that to 2400. That's a good point. Sometimes you guys just assume you can round everything. This is not multiple choice. We want exact answers, so no rounding. So if I have that value there, so see what they're doing, the same thing that I did, is e to the negative 4th there is like 2.17 to the 4th, 1 over that. So it contains mostly reactants. How many of you chose D? Now, you probably chose D because the slide right before you told you to choose D. Do you agree? Are you going to memorize that? If you do, great. Hold on to that information until May. Otherwise, you really need to evaluate your 10 to the 4th and 10 to the negative 4th, okay? So next problem. It says find for the above reaction, delta H equals negative 198. Delta S is negative 188. What is the value of Kp? All right, so we have to use Kp because we are finding our gases here. But if a question gave you, say, a Kc value, you would have to find the Kp value because you're given gases, and vice versa. So if it said to find Kc here, I would have to find my Kp, then use my Kp equals Kc equation with the moles of gas, the delta N. All right, so first thing, if I'm looking for Kp, you have an equation that says K, delta G equals negative RTlnK, so that's where you're going with this. But you first have to find delta G. So this one you should do with a calculator. So I'm going to pause. Put this on here. So the answer is 7.78 times 10 to the 24th. Does that make sense with your delta G value? Ow. Does that make sense? What was your delta G? Negative. So if it was negative, that meant that this should be product favored, which means that K should be greater than 1. Is it? Yeah. Yes. Check that kind of stuff. Make sure that that makes sense to you. All right, next one. For the above reaction, Kc is that, find delta G. So now we're going to use the equation that's been given to you on the AP equation sheet. It gives you delta G equals negative RTlnK, right? Now you're just going to hit that ln button on your calculator to solve this. But here's the problem. I gave you a Kc. What did I just tell you in the last one? You have to use Kp if I gave you gases. And if I gave you aqueous, then you can use Kc. But for delta G, it has to match the state of matter that you're using. Your K value has to match your state of matter. Okay? So try that one. So a few things to just take note of. Your negative sign goes on the outside of this whole thing. So if you're plugging this in, I would plug the negative and then hit parentheses, RT, probably parentheses, LNK, close parentheses. Or if you know how to use your calculator, and you don't need to use parentheses, then you're good. You'll know how to use your calculator after you do all the homework and you get the right answers or you don't, right? So you have the answer key with all the practice problems for this, so you're doing that this weekend.